part 2 of 2 for the higher level examiner's report. Reaction conditions for organic mechanisms. You know what? Just put warm, and more often than not, that's what you have to do. Let's look at 3 others, though, that also need warming. So we have nickel, sulfuric acid, and ethanolic in parentheses. Well, hopefully you remember that nickel is used for hydrogenation of alkenes or alkynes. Sulfuric acid is the catalyst for esters, for making esters, esterification. And ethanolic, well, that's that whole E1, E2 business to get elimination instead of substitution. No real excuse for getting the definitions wrong. Definitions are a type 1 question, which are the easy ones that don't require much of a brain. So get the PDF of the syllabus, Control F to find, and look up the word define. Then you can go through and see the definitions that you need to know. Calculations of rate of reaction. Well, rate of reaction is the change in concentration of reactants over the change in time, or the change in concentration of products over the change in time. So let me give you some data. Let's say there's 3 molar calcium ions at 10 seconds and 1 molar calcium ions at 30 seconds. Well, it seems to be going down, so it can't be products, it must be reactants that we're looking at here. And just by putting the numbers in, 1 minus 3, 30 minus 10, smashing. And don't forget the units, molar per second. Next, percentage uncertainty and precision of experimental data. Well, precision is how close together your data points are. There's me. How old would you say that young man is there? Okay, so if your guesses are going to be close together, like those numbers there, they're precise. But that's nowhere near the real answer. That would involve accuracy. So precise clustered data, accurate close to the accepted value. Percentage uncertainty, well, let's look at this rectangle, 5 by 3 centimeters. There's the uncertainties. So that's going to give me 15 centimeters squared to 2 sig figs. Now, what am I going to do with those uncertainties? Well, let's work out the percentage uncertainty. So it's going to be 0.1 over 5 times 100. That's my percentage uncertainty for the lower part. It's 2%. 0.1 over 3 times 100. It's 3%. Now, what am I going to do with those percentage uncertainties overall? Well, you've got to add them up. So I've got 15 centimeters squared plus or minus 5%. Boiling points of organic functional groups. Well, let's look at methane, methanol, methanol, and methanoic acid. I was stung on the arse by a horsefly and it has methanoic acid. That was the most pain I've ever had concentrated. Oh, moving on. And you can see that as we went along there, they're increasing boiling points, I'll tell you that. So van der Waals, then dipole-dipole, then hydrogen bonds, and the final one has a hydrogen bond and maybe a bit of ionic and some extra van der Waals on the oxygen. No excuses for getting definitions wrong, but the standard electrode potential is the value measured when a standard half cell is attached to a standard hydrogen electrode. The IB says the hydrogen electrode had 0.00 volts, and that's silly, because by definition it's 0, which isn't 0.00. It's a different number. Really. 5 types of electrolysis. Oh, don't make me do it again. Just watch the video. Oi, oi, oi. Bond angles, negative charge centers around the central atom. So 2 charge centers. It's going to be 180 degrees. For 3, it's going to be 120 or less than 120. For 4, that's the classic tetrahedron trigonal base pyramid and bent, depending on if there's 0 lone pairs, 1 lone pair, or 2 lone pairs. Don't forget they're extra repulsive, those lone pairs. 5 charge centers. Looking at 90 and 120. That's seesaw and trigonal base bipyramidal. And 6 charge centers, that's octahedral or square planar. Do you need the 180? Apparently you do. Here's the classic example. Carbon dioxide. Looking at the difference in electronegativity, the carbon-oxygen bond is indeed polar. The bond is polar, but the molecule is non-polar because the bond dipoles cancel each other out. Carbon dioxide is simple molecular, little individual molecules floating around, but silicon dioxide has lots of tetrahedra. Now that's silicon, and to put the oxygen in, you've got to put oxygen atoms in between each silicon. So that's sand, silicon dioxide. It's a giant macromolecule. Why do things conduct electricity? Freely moving charged particles. Anything with freely moving charged particles will conduct electricity. That's why solid salt is an insulator and liquid salt is a conductor. The observable effects of changing the amount of liquid bromine on a liquid vapor equilibrium system. Let's put some bromine in this little egg shape here, and some of it will evaporate to form bromine gas. I climbed up Mount Bromo about 20 years ago. By climbed, I mean someone drove me up there, and it stunk of rotten eggs, which is hydrogen sulfide, not bromine. Bromo is a stench, I think, in Greek. All right then, so there's the equilibrium. If I add some liquid bromine, that's a stress. Le Chatelier said it's going to move to oppose the stress, so it will therefore increase the amount of gaseous bromine. And what's the observable effect? There's going to be more red gas. More vapor, spelt with a U. Determination of pKa, pKa, from the pH curves. All right, let me just draw out a little pH curve there. Oh man, that's awesome. It's near perfect. Not quite. I want to show the buffer region at the beginning, so I'm going to put some extra kind of, there we go, a little plateau there. Alrighty, find the equivalence point, go down to the line, go along halfway, in this case to 8, up and across, and then make this sound, and that's where your pKa is. Normally it's ethanoic acid, so if you're unsure, just look it up in the book and guess that. Oh, jeez. Mechanisms of elimination reactions using curly arrows. Well, you know what? The textbooks aren't necessarily clear that you have to know the mechanisms, but apparently you do. In the video that I did, I've given you the mechanisms, but I said I wasn't sure. It's the same as 1, 2, 3 bang, but instead of SM1, if you have alcoholic hydroxide as opposed to aqueous hydroxide, so if you have the ethanolic, then it's E1, 2, 3, bang. How can I distinguish between the optical isomers experimentally? Well, the crystals slant different ways, but that isn't the answer that they want. Plain polarized light. What makes that? A polarizer. Okay, shine it through your sample, and if it's rotated, if the plane of the polarized light is rotated, then you have indeed an enantiomer in there. A polarimeter will measure the rotation of plain polarized light. And if you forget to say plane, it will be wrong, because other sorts of polarization are available. 3D representations of enantiomers. Again, one of the big textbook got this wrong. So draw out the classic tetrahedron and then make sure that it's a reflection. Make sure that you've drawn the reflection, and that green thing in the middle is the physics sign for a mirror. Yep, those look like reflections to me. Definition of relative atomic mass. And you can tell I buggered this one up because I had to type it in later. The weighted average of the isotopes of an element relative to carbon-12, which has a mass of 12. What are all these 12s? 12 on its own is the relative atomic mass. 12 atomic mass units is the atomic mass, and 12 grams per mole is the molar mass. Explanation of the origin of the colour of transition metal compounds. Alrighty, so there's copper 2+. I'm going to draw out the d orbital, the 3d9. Lovely. And so when ligands come in, for example water, make a dative covalent bond, and it's a lone pair of electrons, and once those ligands have done that, the d orbital will split 3 to 2. And now, when light comes in, multi-wavelength visible light comes in, some of it will be absorbed by promoting an electron to a higher level. And so since energy has been removed from that white light to do that, the light that comes out the other end won't be white. In this case, it will be blue. Determination of reaction rate from experimental data. Well, I'm just going to make up the rate equation. I can only give you the rate equation if I've seen the data. I've just made it up. There is no A, B, and C. Looking at experiment 1 and 2, if I double A, what's my rate going to be? It's going to be 4 because A isn't mentioned in the rate equation. Looking at experiment 2 and 3, everything's the same, but I seem to have doubled B. Okay. So if I doubled B, and B is raised to the first power, that means my rate also has to be doubled. So my rate goes from 4 to 8. The final one's a little tricky because I've changed 2 of the concentrations. Looking at experiment 1 and 4, I've doubled B and I've doubled C. Well, we know the effect of doubling B is going to double the rate. So just accounting for B, my rate's going to go from 4 to 8. And doubling C, get on with it, Thornley, there we go. Well, C is raised to the power 2. So doubling C is going to double squared the rate. That's how I think of it, double squared. So double squared is 4. And so my final rate is going to be 8 times 4, which is 32. Explanation of why low pressure is used. Let me try and draw a nice curve for the mass spectrometer. Couldn't do it. Do it by freehand. An empty mass spectrometer, the ions can zoom through undeflected. But if your mass spectrometer has gas in it, then it's going to jiggle around and it won't have a nice smooth path. And at the end, it will explode. Okay, I made that bit up. There's the hydrogen electron that's been excited already. Now, if that excited electron comes all the way back down to n equals 1, that's going to release ultraviolet light. Big jump, big energy. If it goes down to n equals 2, it's going to release visible light. And if it goes down to n equals 3, it's going to be infrared light. It's a smaller jump, so it's small energy. And we are finished. Good luck in that exam, eh?